Good afternoon, AP Calculus today. So I want to talk about the radius of convergence with the power series. So now let's take a look at the structure right here. So with power series, it's an infinite series. Okay, so the power series, it's an infinite series. So that is such that, which is what? A sub 0 x to the power of 0 plus a sub 1 x to the power of 1 plus a sub 2 x to the power of 2 plus blah 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 plus a sub n x to the power of n. Excuse me. So that means it's being generated with the series, the summation form, sigma, as n equals 0 to infinity of a sub n x to the power of n. So for example, so let's say that we have 1. Okay, so 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the power of 3 over 3 factorial. Well, this one can be written, 1 can be written as x0 over 0 factorial. So let's say that we do have a power series. So the power series either converges at only one point, okay, at one point, converges for all x. Okay, so that would be case 2, or converge over the interval. Okay. So for the given power series, such as like a sub n times x minus c, so where center is at c. So the center at the value of c. So one of the following is true. So the series converge only at one point. Only at one point. Let's say that if r equals 0, the radius convergence, the radius is 0, and the series converges, so this one, that would be all x values, or let's say that all real numbers. If r, it's considered infinity, so let's say that the radius is kind of big, it covers through everything. Okay, so let's say that, so c is right here. Okay, so it could be just right at the point at the value of c. If there's no radius, the radius is 0. Or the radius is like over here to here. Okay, so let's put it this way. With a certain value. So this one would be x plus c. Over here, then that would be x minus c. So this one would be the radius of convergence. Okay, so it's both, consider r equidistant. So let's say r is infinity. It's like all the way, covered all the real number line. Then that'd be for all the x values. If this series converges on the interval, such as like this case right here, interval, the first interval, the second interval, about the value center is c with the radius r. So that absolute value of x minus c is less than r. The series converges. Well, if just sketch the graph, so this one is saying that x minus c, it's less than r, and then x minus c is greater than, well, if that's the other side, it's negative r. To the left, to the right, right? So greater than r, this one is like going two different directions, so the series diverges. So just like going back to what you guys did in Algebra 1, so let's say that you find out two solutions if they intersect. So that means the series converge. Okay? If this one is saying that going two different directions, so one is bounded this way, and the other one is bounded to the other direction, so obviously this one would be diverges. And this one would be converges. Okay, so keep that in mind. So it's got to be less than r. And the reason why that is because the common ratio, you can say that the common ratio r. So we would need to check the endpoint as well. That's right, because sometimes the endpoint would be considered part of the convergence interval as well. So it could be less than, or it could be considered less than or equal to as well. Okay, so we'll find out which case that is. So notice that if r equals 0, so we have case 1, so that means just converge at the point. But if r is infinity, so we have case 2, so that's for all the real number x. So let's do one example like this. So the process of doing this, so the first step, so normally we have to do the limit, the ratio test. So once we do the ratio test, we'll come up with one of the simple structure, and which is considered the representation for the radius. And then we want to set that to the radius. The radius, whether that's less than r or greater than r. Okay? And the other one, we want to set up the comparison with that less than r or greater than r. Okay, so now let's find out. So using the ratio test. So we do know that this one is written as, well, let's just simplify the structure a little bit. So this one is written as negative 1 to the power of n, and then 3 to the power of n times x to the power of n, all over n plus 1 quantity to the power of 1/2. Okay? So you know what? I need more space for this one, so let me just pull this out and put it on the Active Inspire, the Promethean board. Okay, so let me transfer that over here. Okay, so step 1, using the ratio test, so identifying that a sub n using the ratio test. So a sub n, this one, you just rewrite it. So this one, which is 3 to the power of n, x to the power of n, over n plus 1 quantity to the power of 1/2. So using that a sub n plus 1, so we do have 3 to the power of n plus 1, x to the power of n plus 1 over n plus 1 plus 1, which means that it's n plus 2 quantity to the power of 1/2. So the ratio test, that means its limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n. Okay? So in order to have the series absolutely converges, so that means this ratio got to be less than 1. Okay, so now let's find out. So this one, a sub n plus 1, we got 3 to the power of n plus 1 times x to the power of n plus 1, all over n plus 2 quantity to the power of 1/2. Dividing by a sub n, that means we multiply by the reciprocal. Okay, so n plus 1 to the power of 1/2. And then all over 3 to the power of n, x to the power of n. And then obviously this one can cross cancel a little bit. So 3 to the power of n. So 3 to the power of n. So what's left here? Just 3. And then x to the power of n. Cross out with that x to the power of n plus 1. So that's just 3x. And also for this one here, so we can just regroup them. So let's just rewrite it. So absolute value with the limit as n approaches infinity. So right now what we found, its limit, n goes to infinity, and we left with absolute value of 3x times absolute value of n plus 1 over n plus 2 to the power of 1/2. And you may notice that using the L'Hopital's rule for the limit, taking the limit for this one, so this one is 1 to the power of 1/2, it's going to be 1. So for this one here, it's going to be left with 3x, absolute value of 3x, which is less than 1, in order to have a series to be a convergent series. Okay, so 3x, so as you can see that right here, we can just solve for x. So by the time we solve for x, so we want to split it, going back to like what we did in algebra 1 or algebra 2, so negative, positive. So for the negative, it's 3x, it's less than negative 1. And then for the positive, 3x is greater than 1. So that means x is less than negative 1/3. And then x, it's greater than 1/3. Okay, so checking the word carefully. If that's positive, negative, okay, I think I did something wrong here. So this one's supposed to be positive, just rewrite it as original term. So no need to swap the sign. Okay, so let's try that once again. So positive, negative, so algebra 1. Okay, so negative to convert that to its negative, we need to flip the sign for the less than, so it turns out to be greater than or equal to -1. For the positive, we just want to leave it as the way it is without the absolute value. So for this one, x is greater than -1/3. And then the other side here, x is less than 1/3. So just draw down the number line. So in the number line right here, the center, it's right at 0 for this one. So here's the center. So one is what? -1/3. And the other one here is 1/3. So find out the radius of convergence. So that means it's right in between -1/3 and 1/3. Okay, for the interval. Now the thing is that another part of the checkpoint here, we need to make sure that the endpoint, sometimes the endpoint would be considered convergent as well. So in between -1/3 to 1/3, for sure that the series is going to converge for the x value from -1/3 to 1/3. But what about the endpoint? So the next thing that you want to do is to check the endpoint. Okay, so going back to the template. So let's see that. So this series was centered at 0, x equals 0. So the series converged on the interval from -1/3 to 1/3. And however, we still need to check the endpoints of the interval for the possible convergence. Okay, so check the endpoint. So plugging that 1/3 back to the series. Okay, so this one, it's sigma n equals 0. So -3 to the power of n, so I'm just rewriting it, -1 to the power of n, 3 to the power of n, and then what else? And the other one, it's x to the power of n, all over square root of n plus 1. So plugging a number back here, -1/3, so start with x equals -1/3. So we got sigma n equals 0, -1, so 3 to the power of n times -1/3 to the power of n. And then it's all over square root of n plus 1. So for the properties of exponent, so this one, it's under the same power, so 3 times -1/3. So that will give me -1 to the power of n. Okay, so what's left here? So basically this one is just considered -1 times -1 to the power of n, which is 1 to the power of n, so that's 1 over n plus 1 quantity to the power of 1/2. And this one we can certainly, using that the comparison, the limit comparison. So for the limit comparison, you'll see that you try to compare that 1 over n to the power of 1/2. So 1 over n to the power of 1/2, so 1/2 is less than 1 by using the p-series test. So this one is going to be considered a divergent series. Okay, so this one diverges. So if that's the case, so that means the endpoint, it's not considered part of the intervals of convergence. Okay, so now the next one you want to check is that 1/3. Okay, so checking that 1/3, would that be the case? So plug in 1/3 if x equals 1/3. Okay, so sigma n equals 0 to infinity. So -1 to the power of n, and then 3 to the power of n times 1/3 to the power of n. Okay, so this one all over square root of n plus 1. So this one turns out to be -1 over n, and then over square root of n plus 1. And it's an alternating series. And according to the alternating series, so if just do all those tests there, so the limit, Okay, so I need more space, so I'll put it right here first. And the other one I'll just do it on the Promethean board. Okay, so limit n goes to infinity. So 1 over the quantity of n plus 1. So obviously this one goes to 1 over infinity, which is 0. So satisfy the alternating test, the first condition. And then the second condition is that a sub n plus 1. So then that'd be 1 over root n plus 2. Well, if you try to do the test there, it's obviously is less than a sub n, because that you divide it by a bigger number down the bottom. So this one by the alternating series test, so it passed. So it converges, okay? So for this one, converges. So finally, for the intervals of convergence, the radius convergence, so instead of being negative 1/3 to 1/3, so this one would be considered negative 1/3 to 1/3 with the little bracket here, close bracket. So that means the right endpoint, it's also included. So for the radius convergence. Okay, so now let's check the next one. Find the radius of intervals of convergence of the series n times x plus 2 quantity to the power of n over 3 to the power of n plus 1. So now let me take this one to the active inspire. So I'll just do it right there. Okay, so for the radius convergence. So again, follow through the step. So anything that's related with n there. So basically we just want to use that the ratio test. Okay. So this one, rewrite it. So we got n. Okay, let's see. So a sub n, so then that'll be n times x plus 2 quantity to the power of n over 3 to the power of n plus 1. And then a sub n plus 1, then that'll be n plus 2. X plus 2 quantity to the power of n plus 1 all over 3 to the power of n plus 2. Okay, using the ratio test, limit n goes to infinity, absolute value. So n plus 1. X plus 2 quantity to the power of n over 3 to the power of n plus 2. Divided by a sub n, that means you multiply by the reciprocal, so 3 to the power of n plus 1 over n, x plus 2 quantity to the power of n. Okay, so I think I missed n plus 1 here, yeah. And again, this one compare and contrast, so things that we can reduce, simplify, let's just regroup them. So n plus 1 over n, absolute value. And then the other one here, so x plus 2, n, so this one got canceled out. So we got x plus 2. As you can see that the center is right at negative 2. And let's see what else that we have. So the other one, it's 3 to the power of n plus 1 over 3 to the power of n plus 2. So this one would be written as 1 over 3. Okay, so for the limit. And we try to take the limit separately by using the limit property back to what we did in chapter 2, Cal AB. So this one is saying that this one is 1. 1 times 1/3, 1/3. So eventually the limit for this one will be 1/3 times absolute value of x plus 2. In order to have a series being converged to the quantity, so this one, it's going to be less than what? 1. Okay, so let's find out the radius convergence. So it looks like this one's going to be x plus 2. It's less than 3. So now we do know that r is 3, the radius. Find the radius. Okay, that's what we found. And then the intervals of convergence. So interval convergence, separated out. So x plus 2 is less than 3. Let's do the positive first and then the negative. Then the negative would be x plus 2, which is greater than negative 3. So x is less than 1. And over here, x is greater than negative 3 minus 2, negative 5. So draw that on the number line. So center at negative 2. So negative 5, here's 1. And then the radius in between, so r is 3. Over here, r is 3. Okay. So now we're not quite sure about the endpoint, so we need to verify the endpoint. So one is that at x equals -5. And the other one is at x equals 1. Okay, so let's put it to the new page here. So we found the radius, and now we just need to get the intervals of convergence. So it looks like it's going to be from -5 to 1, but we need to verify the endpoint. So verifying the endpoint using the same series. So when x equals -5, so we plug in a number back to the series. So n. So -5 plus 2, then that'll be -3 quantity to the power of n over 3 to the power of n plus 1. So now here's what we can simplify this one to. So n times -1 to the power of n, 3 to the power of n over 3 to the power of n plus 1. Okay, so we need to carry that sigma every time. I know it's kind of tedious, but that's the way to do it. So now what we can find out here, so 3 to the power of n got cancelled, so this one just left with what? 3. Okay, so we got sigma -1 to the power of n, okay, times 1/3, and then times n. Okay, so this one, as you can see that here, and it looks like by the alternating series test, this one is going to be considered divergent, okay? Because we're using the limit as n approaches infinity. So n over 3, it's going to be infinity. It doesn't equal to 0, so it fails the alternating series test. So therefore, it's going to be divergent. And as you can tell, this one, the number is getting bigger and bigger. Okay, so diverge. So that means -5, it's not going to be included. Okay, so it cannot be -5. So now, the next one. So let's verify that the one at -1, x equals -1. Well, because the center is right at -2, so the other side right there, at 1, excuse me. Okay, so going back to that, the other, almost the end point there. Okay, let's check that. Back to the previous page. It is at 1. Okay, so we just verified the 1 at -5. Now verify the 1 at x equals 1. So sigma n equals 0. So n. So we got -1 plus 2, which is 1 to the power of n, over 3 to the power of n plus 1. Okay. So this one can be written as sigma n equals 0. And what we found here, it's well, let's just take out 1/3 first, and then 1/3 to the power of n times n. Again, if n is getting bigger and bigger, so this one, it's going to be considered divergent. Okay, because this one is like well, not the harmonic, but it's like an infinite power series as well. Okay, so n is getting bigger and bigger, so this one also diverges. You can use the comparison test, or you can use the limit comparison. So eventually, so both of those endpoints, they're not included. So the radius convergence, so the radius interval convergence, then that would be from -5 all the way to 1. That's it. Alright, thank you for watching the video today, so I'll see you guys next time. Take care.